we're going to do the common ion effect. Note's going to look a little different because I'm going to do a different problem. Now, I want to compare the common ion effect to me dancing at middle school. In middle school, I didn't dance. If there were other kids dancing, I wouldn't dance. No way. But when I got home, I would definitely dance in my bedroom. I love dancing. Or like if I was away from my peers. This is kind of like what the common ion effect is, in that if I had an insoluble salt, like lead chloride, and I put it in two solutions, one being pure water and one being salt water, pure water and salt water, all right? Remember, salt is NaCl. See this and this, these common ions, it's going to be less soluble. And in this, it's going to be more soluble. Now, lead chloride is pretty insoluble to begin with, but in this, when I've got a common ion, the solubility goes down. So for ionic compounds, solubility goes down in presence of common ion. All right, that's the common ion effect. Okay, here's a problem. This comes directly out of TRO. All right, page 821. And so here we got our molar. What's the molar solubility of calcium fluoride in 0.1 molar sodium fluoride solution? Notice there's our common ion, the fluoride. The calcium fluoride's KSP is this value. Let's look at its, just so we can show how it goes down, let's look at its molar solubility in pure water. Since this is 3 ions, all right, my molar solubility is going to be, my KSP is going to be S times S squared, 2S squared. So this is all going to be 4S to the cube root, all right? And that's going to be, S would be equal to that, all right? So this is molar solubility in pure water, all right? Okay, so then I substituted my KSP value, all right? I would divide this and then take the cube root. I get this. So that's my molar solubility in pure water. This 3.32 times 10 to the fourth. Let's do it in this solution. Now to do this, I'm going to have to set up an ice table, all right? And an ice table, I've got my Ca dissolution into Ca plus 2 plus F negative and 2, all right? And I don't care about this because that's the solid. I'm starting with some of that, none of that, sorry, but I'm starting with 0.1 molar this, all right? There's going to be some change. I'm going to call it X. In the textbook, they use S, but that seems a little confusing because I like X better. It doesn't. You can use either, and this would be 2X. So this is going to be X, and this is going to be 2X. So my KSP is going to be equal to concentration. Oh, I forgot something. Plus 0.1. Okay. There. Now I'm going to substitute this into here. So I get my KSP is X 2X plus 0.1 squared. Okay. And I know my KSP value was that 1 point something. where is it? It's that 1.46 times 10 to the negative 10th equals this. Now, this is really small, so I can cross that out. Too small. That's going to be equal to x. 0.1 squared is going to be 0.01. All right. So I'm going to divide by sides by 0.01. All right. And 1.46 times e to the negative 10th divided by 0.01. I'm going to get 1.5 times 10 to the negative 8th equals x. Oh, sorry. 1.5 e to the negative, and that's my solubility or molar solubility. If you look at the book, it's a little bit different. The calculator rounded because the number is so small. Now, so my molar solubility is less. You can see these two numbers. This one is less, and that's the common ion effect. All right. Let me know if I can help or anything. You have any questions?